Okay, so the chapter 26 radioactivity exam style questions, work solutions. Radioactive nuclides are often injected into patients. Talks about physical half-life. Explain what is meant by half-life. This is really simple. You've got two options. It's the time taken for either the activity to drop by half or number of nuclides to drop by half. So radioactive nuclei to drop by half. Both are acceptable. Effectively, your activity would half if you had half the number of nuclides. State the property of radiation that makes it useful in the treatment of a disease such as cancer, and explain why there are risks associated with the treatment. So we'll answer these in two parts. The first part is, why is it useful? Okay, all radiation is ionizing. Okay, so it turns atoms into ions by stripping electrons. Okay, this can destroy or kill cancer cells. Okay, however, healthy cells can be damaged in the process. Okay, and that last sentence is the risks associated. Okay, three key points: ionization, destroying cancer cells, and healthy cells damaged in the process. So next one's talking about the isotope of uranium-238 and decaying into plutonium-206 by means of alpha and beta decays. Gives us the half-life here, which is going to be useful. So I'll highlight that. Not having a good time, my highlighter. Yeah. And the original number. So 308. Okay, there we go. So at any given time, most of the atoms are either uranium-238 or plutonium-206, and a negligible number of atoms in other forms in the decay series. Effectively, what they've said there, and this will become clear when we do the graph, is the uranium is transferred into plutonium. So as uranium decreases, plutonium will increase. If all your uraniums are being turned into plutonium, as one's going to increase, or one's going to decrease, sorry, the other's going to increase. Okay. Sketch on figure 1 graphs to show how the number of uranium-238 compares to the number of plutonium-206 over a period of 1 to the 10 years. Label your graphs U and PB. Okay. So remember, these two bits of information are going to be key here. Okay. So we've got our initial amount, which is 3 times 10 to the 10 to the 22. We've been told our T half or half-life is 4.5 times 10 to the 9 years. Okay, I'll just rewrite that so we can see it. We've already mentioned in part A what the half-life is. Okay, so we know that after that time, just label it here, we're going to have half the number of original nuclei. Okay, if we're starting with 3 times 10 to the 10, we're going to end up with 1.5. So we've got 1, 2, 3, 4, 5, 6. So here is 1.5. So we know our graph is going to have to cross through that point. It's going to start somewhere up here, and it's going to be an exponential decay. Just remember, our exponential decay graphs look like this. The steepest gradient, that's shocking, steepest gradients at the start, and then it shallows out at the end. But so we'll start out here, going along, making sure we're going through that midpoint there, and then following on. Okay, don't want to quite level out, but along that line. So that's not a very pronounced graph, but we'll go with it. Okay. Fortunately, I can draw these in two different colours. Obviously, you draw these in one colour. Remember, it said as the uranium decreases, the plutonium increases. So all we're going to do is draw exact mirror of this. Okay, so I'll start up here. Look a little bit better. Okay. No, it's not. There we go. And then we want to follow this one down to the same place. Okay. So we should have two graphs with the exact mirror of each other. Okay. So at a certain time t after its formation, sample contained twice as many uranium atoms as plutonium atoms. Show that the number of uranium atoms at the rock sample at time t was 2 times 10 to the 22. Okay, so what we want to do here is look on our graph. Okay, so we're looking at the ratio of plutonium to uranium. Okay, so the number of uranium is going to be, okay, I'm going to have that as the number of uranium. Okay, we know that there's twice as many uraniums as plutonium atoms. Okay, so we've got 2, we have U as the number of uranium atoms, 2 times 3 times 10 to the 22 minus U. Okay, because we're starting with the initial amount of 3 times 10 to the 22. If the amount of uranium atoms we have at the time is U, the number of plutonium we're going to have is double that number minus U. Okay, so we should end up with U, rearrange that, we should get 2U no, sorry, U equals 6 10 to 22. Correct. 3U equals 6 times 10 to the 22. Not very good maths. Therefore, U is 2 times 10 to the 22. So that says calculate T in years. This is going to be using from our formula sheet our the number, the sort of exponential equation, if you will. So we're going to be using N equals N naught E minus lambda T. Okay. Where in this case N is going to be 2 times 10 to the 22. N naught is going to be 3 times 10 to the 22. So that's our original amount. Lambda is going to be, we're going to work out from the half-life. Okay, so again we've got T half is 4.5 times 10 to the 9 years. Okay, so we're going to work out lambda now. So lambda, or the K constant, is ln2 over T half, which is equal to, put that in, 1.54 times 10 to the minus 10 years to the minus 1. Now what we're going to do is plug both these in and take logs of both sides. Okay, so this is, I'll move this up here, give us a bit more room. To rearrange this equation to get T, is going to require a bit of log manipulation. So if we start with N equals N naught E to the minus lambda T, divide both sides by N naught, we end up with N over N naught equals E to the minus lambda T. We take natural log of both sides, so ln N over N naught equals ln E to the minus lambda T. Log rules mean we can bring that minus lambda t down to the front. So we've got minus lambda t ln e. And then n naught. Bring that back down. Ln e is equal to 1. Okay, so we then end up with minus lambda t. Bring it back down here. Minus lambda t equals ln n over n naught. T equals 1 over lambda, minus lambda, sorry, ln n over n naught. Plug all those numbers in, and it comes out as 2.6 times 10 to the 9 years. Okay. Radius of the nucleus of an atom can be determined from electron diffraction. We can show that the radius is r equals r naught a to the 1/3, where r naught is a constant of 1.2 femtometers. Use this to show the density of a spherical nucleus is independent of A. Okay, so what we're going to do is we're going to show that density doesn't depend on A. Okay, so we've got from above R equals R naught A to the 1/3. Okay, volume is proportional to A. Okay, because volume is effectively area times depth. Okay, or if you want to do it more expressively, volume is 4/3 pi r squared, so 4/3 pi r cubed. Okay, which is the same as 4 pi r naught cubed A 3. Okay. So V is proportional to A. Mass is proportional to A. Okay. Therefore, density equals mass divided by volume is proportional to A over A, effectively independent of A. Okay. So, estimate the density of nuclear matter. Okay. So, if we've just talked about density being mass divided by volume, for a nucleus of A nucleons, mass would just be A times mu. Density, volume, as we specified up here, equals 4 pi r naught cubed A over 3. Run out of space here. And therefore, density, I'm going to use the symbol rho, is 3 mu. Okay. 4 pi r naught cubed. Remember, mu is 6 times 10 to the 27, minus 27, apologies, and r naught they've given it above is 1.2 femtometers, so times 10 to the minus 12. Sorry, times 10 to the minus 15, not nanometers. Plug all those numbers in and we get a density of 2.3 times 10 to the 17 kilograms per meter cubed, so incredibly dense. Okay. So now we're talking about alpha particles directed at a thin metal foil. Okay, so similar to the Rutherford experiment, not quite So explain why the incident particle should be in a narrow beam. Okay. Effectively, if we have our alpha particles coming out like this and they're spreading out and we're not getting a narrow beam, when they're scattering, we're going to get the scattering where we want it to be. If I do that in green, so that's where we want it to be. We're also going to get scattering over here and over here, okay, effectively giving us sort of scattering there, but then also sort of scattering in there. So it would sort of give us inaccurate results effectively, because these points here, my incredibly poorly drawn diagram, are effectively going to scatter scatter alphas back into the center to give you sort of unreflective data effectively. So you want to do this to a small collision area, because that's what we want, to reduce uncertainty or increase accuracy in scattering angle. Okay. Metal foil should be very thin to protect too many alpha particles from being absorbed. State another reason for using a very thin metal foil. Please, please, please do not talk about what they've just said. Okay, do not say it's to prevent too many from being absorbed. They've said another reason. Okay, similar to this is we only want one scattering. Okay, so only to be, not a very good sentence, to be scattered once. Again, if we go back to our diagram here, if we had another row here, we'd have our alphas which have been scattered off to the side. Again, they could be re-scattered into the middle, giving us incorrect results, or scatterings that are going straight through could then be scattered off to the side. Okay, so it's all about getting accurate results and accurate measurements. Describe the angular distribution of the scattered alpha particles. So we want to talk about where it will be a maximum, the number of alpha particles, and where it will be a minimum. Okay, the maximum is going to be straight on. Okay, so we're going to get maximum alpha at 0 scattering angle. So where most of them are just going to pass straight on through. Okay, it's really important to read very carefully what the question said here, because it's talking about the number of alpha particles, not the amount that's scattered. Okay, because the amount that's scattered would be a minimum at 0 degrees, but the number of actual alpha particles we're measuring is a maximum at 0. And the inverse of that, we're going to get a minimum alpha at 180 degrees. Okay, and this is our backscattering. So, state and explain 2 deductions made from the scattering distribution about the structure of atoms in the foil. So, we can talk about multiple things here, but the really important part is it's 4 marks, so you're obviously getting 1 mark for the state and 1 mark for the explain, and that's repeated twice, so effectively 2 marks for stating, 2 marks for explaining. Okay. Probably the key one, if we're talking about an alpha particle with 2 protons, is the positive charge of nucleus. Okay. Due to strong repulsion of positive alpha particles. Okay, so that's 2 marks in the bag. So I'll state and I'll explain. The next part is majority or most mass of atom empty. Okay, and this is evidenced as majority of alphas pass through undeflected. Okay, so we're looking at effectively like an open goal scenario where the majority of this is just going straight through and the odd ones kind of bouncing off the crossbar. Could also talk about I could talk about the mass as well. So most mass of atom concentrated at, looks like core, but we all know that's the nucleus, because large enough to backscatter alphas. Okay, you think of the pool analogy. If you smack two pool balls together, you're not going to get one flying back and the other one just remaining stationary. Okay, this would be like cracking a pool ball into the side of a building. Okay, the building's not going to move, but the ball's definitely going to go back the other way. Okay, so you know it's got a lot of mass because momentum is conserved. So now we're talking about the paths of these actual alphas as they're deflected. Obviously our field is going to be, oh, these look like photons. Our field is going to be increasing radially. Okay, so the strength of our field is going to be getting weaker as we go out. So the maximum deflection is going to occur here, closest. Okay, it's going to feel the strongest repulsion of the nucleus. Next weakest or next strongest, it's in the middle. It's going to be there, and the weakest one, still deflected slightly, is going to be there. Okay. Radioactivity experiment. Background radiation is taken into account and corrected count. One source background radiation is the rocks on which the laboratory is built. Take note, everyone. They've talked about the rocks. Give two other sources of background radiation. Source one, do not say the rocks. They have just said the rocks up there. Okay? Do not mention the rocks. The easiest one is going to be radon gas. Okay, next one, solar radiation. Okay, you could talk about nuclear testing. Okay, the nuclear weapons testing caused quite a lot of background radiation in the atmosphere. You can actually look at graphs of that after they organised a sort of testing treaty to stop nuclear testing. The amount of radioactive stuff in the atmosphere dropped sharply. Talk about carbon-14 in organic matter. You could have leaks. You need to specify this, so this could be like Chernobyl. I think that's spelled right. Fukushima. Okay, you need to be specific with those leaks. But as a whole world, just do not say radioactive rocks, because they've already said it. Okay, both of those for 1 mark. Next, we're talking about a gamma ray detector with a cross-sectional area. Okay. Talks about the corrected count rate. Assume that this source emits gamma rays uniformly in all directions. Show the ratio, the number of gamma photons incident on detector, and the number of gamma photons produced by the source is about 4 times 10 to the minus 3. So what we're looking at here is the ratio of the detector to the surface of the sphere. Okay, so if I were to draw this, we'd have, let's go for green. Come on, okay. We'd have our source, okay, and then we'd have our, let's try to fix circle, our sort of imaginary sphere of where that's going out. Okay, so it's going out radially in all directions, and then we'd have some cross-sectional area there. Hey, it's a bit like Death Star. Okay, so we're looking at the ratio of that, because obviously a proportion of that will be absorbed. The vast majority, however, will be going off in all directions. Okay, so the area of the sphere will be, the surface area of the sphere will be 4 pi r squared, and obviously the area, so surface area, the area of detector, actually let's change that, area of the sphere, so subscript, and area detector will obviously be 1.5 times 10 to the minus 3, okay, meters squared. And sub in our number, we're going to get 4 pi 0.18 squared. The ratio of those, the ratio of AD over AS is 1.5 times 10 to the minus 3, not minus 13, that'd be quite a bit smaller. 10 to the minus 3, 4 pi 0.18 squared comes out as 0.0037, so around 4 times 10 to the minus 3. Okay, so just comparing the ratios of those there. Next, gamma ray detector detects 1 in 400 gamma photons incident on the facing unit. Detector, calculate the activity of the source. So it's telling us it detects 1 in 400 of the gamma rays incident. So effectively we need to say that there's 400 more there than we're detecting. Okay. If there's 400 more than we're detecting, we also need to mention the area over which we're detecting. Because remember, we said here that the ratio of the number of photons produced compared to the number incident is around 0.04. So we're measuring 0.4% of what it's actually doing. Okay, so the activity will be our measured value, which if we go up here, okay, 0.62. Okay, times by 400, because again we're only measuring 1 in 400, so we want to get that corrected, and then divided by that factor, which is 0.0036. Okay, so 368, we're going to use our actual calculator value rather than 37. That then comes out as 67,400. Okay. Our units for activity are becquerels. Okay, BQ. Okay, becquerels is just a disintegration per second. A second, but really you want to be using becquerels. Calculate the corrected count rate when the detector is moved 0.1 meter further from the source. So in this case we're looking at our inverse square law. Okay, so again we're saying that the sort of intensity of radiation will be proportional to 1 over r squared. Okay, so as r doubles, intensity will quarter. Because again, we're looking back at this radial shape here. So another sphere here would be much greater area for it to spread out and sort of diffuse across. So the original intensity, we can say the original intensity is equal to 1 or some sort of k value, some constant over r1 squared, and the corrected, or the second intensity, is equal to, so that k, same factor, over r2 squared. Okay, so this is what we're interested in. Rearrange both of those to get K and then equate them. So we end up with I1 R1 squared equals I2 R2 squared. So I2 R2 squared. Rearrange to get that, and we have I2 equals I1 R1 over R2 squared. We'll take the square outside the bracket. Okay, I1 is 0.67, no, 0.62, I remember, let's double check that. Yeah, 0.62. The radius before is 0.18, and the radius after is 0.28 because it's 0.1 more, 0.28. Square all of that, and it comes out as 0.26. So figure shows how the count rate C recorded varies with thicknesses. Okay, so we're talking about the attenuation for a given thickness now. Use data from figure 3 to explain, also show that the count rate C decreases exponentially with absorber thickness. Okay, so when we're talking about an exponential decrease, what we're saying, just draw this here, the gradient at the start, delta y over delta x, is bigger for this portion than it is for this portion. Okay, that's the reason the slope goes down, because the gradient is decreasing. So to show that, we want to find the gradient at some point, okay, for two given x's. So if we say, okay, let's go for the first two here. So our delta x is equal to 2 millimeters, remember in our units. So we'll take these two here. Our delta y is, just drawing over the line, it's not ideal. Drawing over the line, so it'd be about 13. So that's going to be 13,250 minus 1,600. Sorry, 1350. Okay, which comes out as 250. Do the same again from 10 to 12. There, delta x again, same thing. 2 millimeters. Our delta y on the other hand is about 680 minus 560. Comes out as 80. No. 120. Okay, so our gradient at this point is going to be 250 over 2, so M1. M2 is going to be 120 over 2, okay, ignoring all other factors and stuff like that. So we're getting 125 and 60. Okay. Gradient at start, just put on graph, equals 125. All the units of these, counts per second, 1 millimeter. Gradient end on graph equals 60 counts per second per millimeter. Okay, so we're showing that we've got the ratio of these two, therefore gradient decreasing as x increases, what are these? Exponential. Next, talking about the intensity of it decreasing. Okay. So I over I naught is E minus ux. Okay, we're looking at the exponential change of intensity with x, which funny enough is what we've got on our graph. So our gradient of the graph is approximately equal to I over I naught approximately equal to 0.5. So if we're looking at the half thickness, okay, half thickness intensity, if we're looking at this, the half thickness would be 6. So going up this point here, let me draw that in a different colour. It can get a bit confusing. Okay, so we're just looking for whatever the intensity will be at half the thickness there. So we're getting about